Hello, my dear students. Today we are going to talk about redox reactions. Now, redox reactions are so commonplace. They take place in so many everyday things. Every time you see something burn, that is called a combustion reaction. It is actually just a chemical reaction happening that gives out light and heat, and that is a redox reaction. The fuel is burning in oxygen to become carbon dioxide and water, and that is simply a redox reaction. Um, Rusting, it takes a lot longer to happen than an explosion or a fire. That's a very, very fast reaction, a very fast redox reaction. But something like rusting, that is a very slow redox reaction. Have you ever noticed when you cut an apple, very quickly it starts to go brown? That is the proteins in the apple, and they are being oxidized. They are undergoing a redox reaction. They're reacting with the oxygen in the air, and that brown is actually melanin that's being produced. It's the same melanin that determines how dark your skin color is. If your skin color is dark, you've got a lot of melanin in your skin. And if your skin color is very pale, then you don't have a lot of melanin in your skin. And that brown that you are seeing is a defense mechanism. When you've cut through the apple, you've actually injured it, and the melanin is produced to try and protect the apple. So that is an oxidation reaction that's happening. And of course, oxidation and reduction have to happen together. Um, Plants and humans have existed on the planet for a very, very long time because we complement each other beautifully. Plants take carbon dioxide from the air and they turn it into glucose, give out oxygen. So photosynthesis and respiration, which is the process that you do in your cells to take that oxygen and the glucose and you put them together to make energy for yourself. They are the opposite equations of each other, so they complement each other very, very nicely. And both of those are redox reactions. So, what is the definition of a redox reaction? You'll see that it's made up of two words, redox. It's made up of a re, which stands for reduction, and reduction, and ox, which is oxidation. And we put it together and it makes redox. And the reason why is because reduction cannot happen without oxidation, and oxidation cannot happen without reduction. The very simplest term is that reduction is when a species loses oxygen, and oxidation is when it gains it. So, of course, oxygen can't just be magicked from somewhere. It has to have existed before in the chemical reaction. So, the oxygen is just leaving one species as part of the chemical reaction and is being taken on in the new compound that's formed by something else. So let's have a look at how that works in practice. Let's see if we can identify what has been reduced and what has been oxidized in a chemical reaction. So let's just take the first one here. We've got copper oxide reacting with hydrogen to produce copper and water. Redox can only happen to, reduction and oxidation can only happen to things on the left-hand side. We use the right-hand side here to find out what has lost and what has gained. There should be a little plus in there. So some people fall into the trap of saying, oh, the copper's been oxidized. Well, there's no copper on this side, there's just copper oxide. Okay, so you have to be careful when you say what's been oxidized and what's been reduced. So you can see here that the copper has lost oxygen. It was copper oxide and now it's turned into copper. And that the hydrogen here has gained that oxygen. So we say the CuO has been reduced. And we say that the H2 has been oxidized. We could go further and we say the CuO has been reduced to copper and the H2 has been oxidized to H2O. Let's try another one. Magnesium plus copper oxide makes magnesium oxide and copper. Well, the magnesium on this side has gained the oxygen, and the copper oxide has lost the oxygen. So we say the Mg has lost the oxygen, so it's been has gained the oxygen, so it's been oxidized to MgO, and the CuO, or the copper oxide, has been reduced to copper. Let's try one more. If you're thinking, really, it's that easy? For this definition of redox, it absolutely is. Next definition of redox, we're going to ramp it up a little bit. It's still just as easy to identify, but you're right. If you're sitting here thinking this is easy, you're absolutely right, it is. The H2 has gone to H2O, and the O2 has also gone to H2O. Now you might be thinking, hang on a minute, there's only one product at the end. What's happened here? Well, H2, did it have any oxygen to start off with? The answer is no, it didn't. I do apologise, my pen had a bit of a barney there. The H2 didn't have any oxygen to start off with. It had oxygen at the end because it was turned into H2O, so it must have been oxidized to H2O. And the O2, well, you might be sitting here thinking, well, how can oxygen lose oxygen? That's crazy. It had oxygen to start off with because it was oxygen, and then it's gone to oxygen over there. Hang on, how does that work? Well, the O2 has actually lost. You see, there was 2 oxygens in the molecule, and now there's only 1 oxygen in the molecule over here. So believe it or not, the oxygen has indeed lost oxygen. It has been reduced to H2O. So remember, you cannot have oxidation without reduction. Calcium and oxygen, well, let's have a look. Calcium has gained oxygen. Again, the oxygen has lost the oxygen. So calcium has been oxidized, and O2 has been reduced. Both have been oxidized to CaO. And this one being reduced to CaO. You may well think, well, this equation isn't balanced. Well, it's not. You could just put a big 2 there, and it would be balanced. Another 2 there. Okay, if that's really bothering you. But we're not too fussed about it. It doesn't matter whether the equations are balanced so much, because it's very easy to see in this one which has gained and which has lost oxygen. Again, this one's not balanced, so we could balance this one. See, they're very similar equations here. Magnesium and oxygen, as you can see, the magnesium has gained the oxygen, so it's been oxidized to MgO, and the O2 has been reduced to MgO. It really is that simple, folks. You just look at the equation, you look at what's lost oxygen, you look at what's gained oxygen from the reactants, and you do that. You tell by looking at the products. Has it gained or has it lost? I hope that was helpful.